Welcome to Chemistry, Acid-Base Titration Curves. A titration is one of the most powerful analytical techniques in chemistry, allowing us to determine the concentration of an unknown acid or base by reacting it with a standardized solution. The titration curve, a graph of pH versus volume of titrant added, reveals the fundamental acid-base behavior of the system. In this presentation, we will explore titration curves for strong acid, strong base, weak acid, strong base, and polyprotic acid titrations. We will learn about the equivalence point, half equivalence point, and buffer region. By the end, you will be able to interpret any titration curve with confidence. A titration experiment involves the controlled addition of a solution of known concentration, called the titrant, from a burette into a solution of unknown concentration, called the analyte, in an Erlenmeyer flask. The titrant is added slowly while the solution is stirred, and the pH is monitored continuously. The goal is to reach the equivalence point, the exact volume at which the moles of titrant added are stoichiometrically equal to the moles of analyte present. For an acid-base titration, this means the number of moles of H+ from the acid equals the number of moles of OH- from the base. A good indicator is chosen so that its endpoint coincides with the equivalence point. The titration of a strong acid with a strong base produces the classic S-shaped titration curve. Consider adding 0.100 molar NaOH to 50 milliliters of 0.100 molar HCl. Initially, the solution contains only HCl, which fully dissociates, giving pH equals 1.00. As NaOH is added, the pH rises gradually. At the equivalence point, all acid and base have reacted to form NaCl and water, making the solution neutral with pH equals 7.00. After equivalence, excess OH- accumulates and the pH rises sharply. Titrating a weak acid with a strong base produces a more complex curve. Consider adding 2.100 molar NaOH to 50 milliliters of 0.100 molar acetic acid. Initially, the pH is calculated from the Ka expression, giving approximately 2.87. As NaOH is added, a buffer solution forms consisting of undissociated acetic acid and acetate ion. In this buffer region, the pH changes gradually. At the half equivalence point, the concentrations of acid and conjugate base are equal, so pH equals pKa, which is 4.74 for acetic acid. This directly gives the pKa of the weak acid. At the equivalence point, all acetic acid has been converted to acetate, a weak base, so the pH is above 7, around 8.7. Polyprotic acids have more than one acidic proton to donate. Their titration curves display multiple equivalence points, one for each proton that can be neutralized. For phosphoric acid, a triprotic acid, the curve has 3 distinct equivalence points and 3 buffer regions. Each deprotonation step has its own Ka value, and successive Ka values differ by several orders of magnitude because removing a proton from a negatively charged species becomes progressively more difficult. Each equivalence point can be identified by a separate pH jump. An acid-base indicator is a weak acid whose conjugate forms have different colors. The color change occurs over a pH range of approximately pKa of the indicator plus or minus 1. For a strong acid-strong base titration, the pH jump spans about 3 to 10. So many indicators work. Phenolphthalein changes from colorless to pink around pH 8.2 to 10.0, and methyl orange changes from red to yellow around pH 3.1 to 4.4. For a weak acid-strong base titration, the equivalence point is above pH 7, so phenolphthalein is a good choice. For a weak base-strong acid titration, the equivalence point is below pH 7, so methyl orange is appropriate. Choosing the wrong indicator leads to significant error. The buffer region of a weak acid-strong base titration curve is the relatively flat portion before the equivalence point, where significant amounts of both the weak acid and its conjugate base are present. In this region, the solution resists pH change because added OH- reacts with HA to form A-, and the pH is controlled by the Henderson Hasselbalch equation. The most important point is the half equivalence point, where exactly half of the weak acid has been neutralized. At this point, the concentration of the weak acid equals the concentration of its conjugate base, so pH equals pKk. This provides a direct experimental method for determining the pKa of any weak acid. Calculating points on a titration curve requires applying the right equation for each region. Before any titrant is added, the pH depends only on the initial acid or base concentration. In the buffer region before equivalence, we use the Henderson Hasselbalch equation. pH equals pKa plus log of moles of base added divided by moles of acid remaining. At the equivalence point for weak acid-strong base, we calculate the pH of the conjugate base solution using Kb equals Kw divided by Ka. After equivalence, pH is determined by excess titrant. These calculations form the foundation for interpreting any titration curve. Let us now examine the anatomy of a titration curve. This SVG diagram shows the characteristic features. On the vertical axis, we have pH, ranging from 0 to 14. On the horizontal axis, we have the volume of titrant added in milliliters. The curve starts at a low pH for a strong acid, then rises gradually before the steep titration jump near the equivalence point. After equivalence, the curve levels off at a high pH. The equivalence point is marked at the center of the steep region. Notice the buffer region before equivalence, where the curve is relatively flat. Understanding these features is essential for interpreting any titration data. Quiz question 1. What is the pH at the equivalence point of a strong acid-strong base titration? Option A, 1. Option B, 7. Option C, 14. Option D, it depends on concentration. The correct answer is B, 7. At the equivalence point of a strong acid-strong base titration, the pH is exactly 7 at 25 degrees Celsius because the salt formed does not undergo hydrolysis. Neither the cation nor the anion reacts with water, so the solution remains neutral. Quiz question 2. At the half equivalence point of a weak acid titration, what is true? Option A, Ha concentration equals 0. Option B, A minus concentration equals 0. Option C, HA concentration equals A minus concentration. Option D, pH equals 7. The correct answer is C. At half equivalence, exactly half of the weak acid has been neutralized, so HA and A minus concentrations are equal. Substituting into the Henderson-Hasselbalch equation gives pH equals pKa. This provides a direct experimental method for determining the pKa of a weak acid. Quiz question 3. Which indicator is best for titrating a weak acid with a strong base? Option A, methyl orange with pKa around 3.7. Option B, phenolphthalein with pKa around 9.3. Option C, bromophenol blue with pKa around 4.0. Option D, thymol blue with pKa around 1.7. The correct answer is B, phenolphthalein. For a weak acid-strong base titration, the equivalence point pH is above 7, typically 8 to 9. Phenolphthalein changes color in the pH range 8.2 to 10.0, which coincides with the steep region. Methyl orange changes color far too early. Quiz question 4. How many equivalence points does phosphoric acid have in a complete titration? Option A 1, option B 2, option C 3, option D 4. The correct answer is C 3. Phosphoric acid is triprotic with 3 acidic protons. Complete titration requires 3 equivalents of base, producing H2PO4-, HPO42-, and PO43- successively. Each deprotonation step has its own equivalence point. Quiz question 5. A 25 milliliter sample of HCl requires 32.4 milliliters of 0.150 molar NaOH to reach the equivalence point. What is the concentration of HCl? Option A, 0.116 molar. Option B, 0.150 molar. Option C, 0.194 molar. Option D, 0.250 molar. The correct answer is C, 0.194 molar. Using M acid times V acid equals M base times V base with a 1-to-1 mole ratio, we have M acid times 25.0 equals 0.150 times 32.4. Solving gives M acid equals 0.194 molar. This calculation is the fundamental use of titration data to find an unknown concentration. Problem 1. Finding concentration from titration data. 35 milliliters of 0.200 molar NaOH is needed to neutralize 50 milliliters of sulfuric acid. Step 1. Write the balanced equation. H2SO4 plus 2 NaOH yields Na2SO4 plus 2 H2O. Step 2. The mole ratio is 1 to 2. 1 mole of sulfuric acid reacts with 2 moles of NaOH. Step 3. Calculate moles of NaOH used. 0.200 molar times 0.035 liters gives 7.00 times 10 to the negative 3 moles. Step 4. Moles of H2SO4 equals half of that, 3.50 times 10 to the negative 3 moles. Step 5. Concentration equals moles divided by volume. 3.50 times 10 to the negative 3 divided by 0.050 liters equals 0.0700 molar. The final answer is 0.0700 molar H2SO4. Problem 2. Determining the pKa of a weak acid from titration data. 50 milliliters of 0.100 molar weak acid HA requires 25 milliliters of 0.200 molar NaOH to reach the equivalence point. At 12.5 milliliter of NaOH, the pH is 4.60. Step 1. The equivalence volume is 25 milliliters. Step 2. Half of that is 12.5 milliliters. Step 3. At this volume, the pH is measured as 4.60. Step 4. At the half equivalence point, the concentrations of HA and A- are equal, so pH equals pKk. Step 5. Therefore, pKa equals 4.60. Step 6. Ka equals 10 to the power of negative 4.60, which equals 2.51 times 10 to the negative 5. The final answer is pKa of 4.60 and Ka of 2.51 times 10 to the negative 5. Problem 3. Calculating pH before the equivalence point. 50 milliliters of 0.100 molar acetic acid with Ka equals 1.8 times 10 to the negative 5 is titrated with 0.100 molar NaOH. Find pH after adding 10 milliliters of NaOH. Step 1. Initial moles of HA are 0.100 times 0.050 equals 5.00 times 10 to the negative 3. Step 2. Moles of OH minus added are 0.100 times 0.010 equals 1.00 times 10 to the negative 3. Step 3. OH remaining equals 5.00 minus 1.00 equals 4.00 times 10 to the negative 3 moles. Step 4. A minus formed equals 1.00 times 10 to the negative 3 moles. Step 5. Using the Henderson Hasselbalch equation, pH equals 4.74 plus log of 1.00 divided by 4.00, which equals 4.74 minus 0.60, giving a pH of 4.14. Problem 4. Finding the pH at the equivalence point of a weak acid-strong base titration. 50 milliliters of 0.100 molar acetic acid is titrated with 0.100 molar NaOH. Ka is 1.8 times 10 to the negative 5. Step 1. The equivalence volume is 50 milliliters. Step 2. Total volume at equivalence is 100 milliliters. Step 3. The concentration of acetate is 0.0500 molar. Step 4. Kb equals Kw divided by Ka equals 5.56 times 10 to the negative 10. Step 5. OH minus concentration equals 5.27 times 10 to the negative 6 molar. Step 6. POH equals 5.28, so pH equals 8.72. At equivalence of a weak acid-strong base titration, the pH is always above 7. Problem 5. A polyprotic acid titration analysis. 25 milliliters of 0.200 molar phosphoric acid requires how many milliliters of 0.300 molar NaOH to reach the second equivalence point? Step 1. The second equivalence point means 2 protons have been neutralized per molecule of H3PO4. Step 2. The balanced equation is H3PO4 plus 2 NaOH yields Na2HPO4 plus 2H2O. Step 3. Moles of H3PO4 equals 5.0 times 10 to the negative 3. Step 4. Moles of NaOH needed equals 1.0 times 10 to the negative 2. Step 5. Volume of NaOH equals 66.7 milliliters for the second equivalence point. The final answer is 66.7 milliliter of NaOH. Let us bring everything together in a comprehensive review. Acid-base titration curves are graphical representations of pH change during neutralization. 5 key concepts form the foundation. First, the equivalence point is where moles of acid equal moles of base, and its pH depends on the strength of the acid and base involved. Second, the half equivalence point reveals the pKa of a weak acid, because at that point, HA and A- concentrations are equal. Third, the buffer region before equivalence resists pH change and follows the Henderson Hasselbalch equation. Fourth, polyprotic acids display multiple equivalence points, one for each proton. Fifth, indicator selection must match the pH jump of the titration. The key formulas to remember are MAV, A equals MBVB for monoprotic titrations, pH equals pKa at half equivalence, and the Henderson Hasselbalch equation. Thank you for learning with us.